So yeah, so multiplying by real numbers literally is just a stretch. That's all I want you to think about from a geometric perspective. All right, great. So if we then move on then, let's think about the different powers of complex numbers that we could have. All right, so I've put them up on the screen there, but I want to actually derive them for yourself. So if I take the complex number I, now just remember I, can anybody remember what this is actually equal to? Good, yeah, it was all to do with if we wanted to take the square of a negative number. Before last week we didn't know how to do that. We just like, math is broken, let's just ignore it, right? But now we actually have a way of systematically dealing with it. So if I take I and raise it to the power of 0, what's this equal to?
1.
It's just equal to 1. Any number raised to the power of 0 is 1. Right, we've seen that in other real numbers. It makes sense that square root of negative 1, which is just a number we're supposing, raised to the power of 0 will also be equal to 1. Okay. What do you think I to the power of 1 is going to be equal to?
I.
Just I. Any number raised to the power of 1 is just itself, right? So that makes sense. Okay, what about I squared?
I squared.
Okay, so deal with this. Square root of negative 1. If we square it, fantastic, we get negative 1, right? Squaring, square rooting, they undo each other. So we just get a negative 1 there. What about I cubed?
Minus I.
Good. Why did you say that?
Minus 2 times I. Sorry.
Minus 1 times I.
Yeah.
Yep.
I squared times I.
Absolutely right. So you're literally just saying, well, I cubed. I'm not sure what it is at the moment, but I realised just thinking about my powers, I could just take I squared, which I know is just negative 1, and times it by I. That would still be I cubed. Yeah?
Yeah.
So in other words, if I know that I squared is negative 1, and I know I, it's just I, right? This is just going to be negative I. Make sense? All right, keep going then. What would I to the power of 4 be?
1.
Just going to be equal to 1. Why is it going to be equal to 1?
I squared plus I
Times?
times I squared.
Excellent. Yeah, so you say, okay, I can make this out of I squared times I squared. Perfect. I squared is negative 1. I squared is negative 1. Times together. Negative 1 times negative 1 is just positive 1. Great. What would I to the power of 5 be?
Minus 1.
Not quite, actually.
You start the cycle again because you after 4
So minus I.
you can merge your I squares together.
Absolutely right.
And then repeat.
Yeah, so the answer is going to be I. You're right, I will come on to that in just a second. But yeah, you're absolutely right. If you take I to the power 5, you can treat that as I to the power 4, which I know is 1,
Yeah.
times by I. Right, so 1 times I, just I again. Okay. Now in fact, and John Sebastian, you're absolutely right here. If I consider I to the power of 6, what do you think it's going to be equal to? Not actually calculating it, but just looking at the pattern, what do you think it's going to be equal to? Negative 1. And what about I to the power 7? Good, minus I. And what about I to the power of 8? 1, fantastic. And so on and so on and so on. So what you're noticing then is that every 4, you basically get a repeat. Okay, so I to the power of 0 is 1, I to the power of 1 is I to the power of 2 is negative 1, I to the power of 3 is negative I, and then as soon as you get back to I to the power of 4 again, you're back to 1. And then it goes again. So 1, I, negative 1, I, negative I. So it's exactly the same pattern as you had before. That makes sense? Right? Now, obviously, we've done the sort of calculation in the algebra just by thinking about what happens if we take square root of negative 1, raising it to different powers. But what would this look like geometrically? Because I think it's easier to visualize geometrically.
And then just do like 90 degrees every time.
Perfect. Yeah, absolutely. So if we have a look at this, bearing in mind that all we're literally doing here is multiplying basically versions of I with itself. Yeah? So because there's multiplication going on in the background, we've just seen that with multiplying real numbers together, we get that stretch which happens. Let's see what happens when we take I and multiply it by versions of itself. So you can see here I've got I to the power of 0 equals 1. And you can see that this is just represented by a dot. on the right hand side of your screen. Okay, that's just at 1 on the Argand diagram. Now if I multiply by I, look what happens. Can you see it jumps up there to positive I, right? And if I multiply by I again, it jumps down to negative 1, jumps down to negative I when I multiply by I again, and then we're back to 1. And actually if I keep going, can you see that what's happening every single time is I'm literally just multiplying, or I'm literally just rotating through pi by 2 radians, right? Hence the reason why every 4 it repeats, okay? Because I literally have 4 quadrants, or 4 places on the real axis that it can hit. Therefore, because I'm just literally going round and round and round, I get repeats every 4, right? So what that means then is that if I want to consider something really big, like I to the power of 2021, okay, current year, okay, all I have to do is just think, well, how many times have I rotated through that cycle of 4? Yeah? So if I take 2021 and divide it by 4, now of course what I'm interested in is not what that is equal to, what I'm interested in is what's the remainder, right? So if I take 2021 and divide it by 4, what do I get?
1.
Just get 1, yeah? Because 2000 divided by 4 goes in neatly, 20 divided by 4 goes in neatly, so I'll just have that 1 left over, yeah? So therefore I can say that this should just be I to the power of 1, come over here, it's just I. Make sense? Yeah, cool.
So you did modulo.
Exactly, I'm doing modulo arithmetic, okay? So if you've ever thought about this, this is sometimes called clock arithmetic. It's basically you're thinking about how many times this goes into here, and crucially you're thinking about what the remainder is. The reason why it's called clock arithmetic, because if you think about it, think about a clock, it's 1, 2, 3, 4, okay, so 12 kind of positions on the clock. What I'm literally asking here is how many times have I rotated around the clock? Okay, so if I, for example, divide by 12, mod 12, right, all I'm thinking about is how many times have I rotated around the clock, and then crucially, what's left over, yeah?
So it's just the way you written it, I was a bit confused.
That's fine. Yeah, fine. So yeah, that's not equal to 1. Of course it's not equal to 1. But yeah, the remainder is 1. Absolutely. That's the thing which I'm looking for. So yeah, it's modular arithmetic if you like. But if you prefer, just think about this. Every time you multiply by I, you get that rotation of pi by 2.